Okay, so now what I'd like to do is use what we saw in the last lecture, which was really about experimental observations. That is, if I put a mass on two springs, I double the stretch, and therefore I reduce the effective equivalent spring constant by half. So, with that said, what I really like to do is sort of analyze this from a first principles approach and see what we get to. So, let's take what we've learned, and that is if I put a mass on two springs in series, I increase the stretch by the sum of the two stretches, S1 plus S2, as you can see here. What I also have is that the force on each individual spring is the same. Right, so this spring sees the mass times the acceleration due to gravity, and this spring also sees a mass times the acceleration due to gravity. And so as a consequence, I can say that the force on spring 1 is equal to the force on spring 2. They're equal to each other because they are experiencing the same exact force. And so what that allows me to do is equate the spring constant times the stretch for each individual spring. So I can say that S1 times minus K1 sub S is equal to minus K sub S for spring 2 times S2. And so that allows me to write everything in terms of either S1 or S2. So S2 is equal to, well, K1, K1, K2 times S1. Okay. So now if I think about the force on both springs together, I can write that relationship as the force on the equivalent spring, or the total of the two, I'll just call it F sub S, on the new spring that I've created, is minus K, and I'm going to call this the equivalent spring constant, KEQ, that outlined over there, times, well, the total stretch in the system. And so now I can write S1 plus what is now K1, the original, K2, the original, times S1 again. So now I have everything in terms of the stretch of S1. So now I can write the force, S, and I've dropped my L hats, so I can probably get rid of my force vectors here, because it's one-dimensional. I can do this in a vector form, but I don't necessarily have to. So now let's write it as, well, what do we have? We have F1 is equal to, so let's do this, K equivalent minus K equivalent times, okay, this becomes K1 plus K2 over K1, K2 over K2 times S1. Okay? And so, what we can write is that this is equal to, actually, it's equal to either F1 or F2. It all experiences the same force. The force on 1, which is equal to minus K1 S 1. Okay, so now I can get rid of my S1s, and now what I have is K equivalent is equal to, well, it's equal to, I'm going to write it out first. I'm going to say K equivalent times K1 plus K2 over K2 is equal to K1. I've dropped my minus signs, they're on both sides. And so K equivalent is now equal to K1 times K2 over K2 plus K1. And when I have that, I can now find that each term, if I flip this over, 1 over k equivalent is equal to 1 over k1 plus 1 over k2. Be consistent with my writing. And we have this. And so if I want to know the equivalent spring constant for two springs in series, I can write that it is equal to 1 over that value is equal to 1 over the first spring constant plus 1 over the second spring constant. And so, for example, if k1 is equal to k2, what I get is well, I should have 1 over k equivalent is equal to 1 over k1 plus 1 over k2. 1 over k equivalent is equal to 2. I'm sorry, I'm being very inconsistent. k1, k2, k1, k1. And so 2 over k1, which is if I take the inverse of this, k equivalent is equal to k1 over 2, which is what we found before.